As you saw from the emails, our colloquium speaker for today, Jessica Zebrowski, has come down with something, and so won't be able to visit. And I know many of you wanted to meet with her, and many of you recommended her as a speaker. She will be here in spring, coordinating that visit with Kirk. So she will be down in March, we think next year. So hopefully nothing permanent. Normally we'd have just canceled colloquium, but we are extraordinarily fortunate, partly because we are at the University of Illinois and have a incredible contingent of wonderful researchers come through fairly regularly, to have today Dr. Nicholas Kern. Nick did his undergraduate work at the University of Michigan before moving to UC Berkeley for his master's and his PhD. He was then a Pappalardo Fellow at MIT. At the same time that Jesse Shelton, next door in physics, was visiting, which is why he will also be doing the ARC seminar tomorrow. And now he is a Hubble Fellow and has been working on 21 centimeter and ionization, and will tell us about the high redshift universe and all of his work. So it's actually somewhat related to the stuff that Jessica might have talked about. They were supposed to meet with each other.
Yes, yeah, I was very much looking forward to touching base with him, but we'll have to do it another time.
Exactly.
Okay.
And we're glad to have you. Thank you again for stepping in.
Appreciate it.
Please take it away.
Thank you, Gautam. Yeah, thank you so much. So I'm Nick. I'm happy to be here to talk to you a little bit today about my work. Put this talk together a little last minute, so apologies if it's a little hodgepodge, but I'm talking today about the high redshift universe and some of my work doing 21 centimeter, like Gautam said. All right, so in the 2020s, what do we know about our universe, right? Well, we've established kind of our LCDM paradigm set largely by early universe probes of the high redshift universe, looking at the afterglow of the Big Bang, and late time probes looking at the formation of the cosmic web and the accelerating expansion of the universe. However, there's still a lot we don't understand, and some might say that we are approaching a post-LCDM universe, particularly with the recent DESI results looking at evolving dark energy. But suffice to say, it is clear that there's a lot we don't understand. And what's also clear is that there's a lot that we have yet, there's a lot of cosmological information that we have yet to harness to try to answer some of these questions. So what's going on with inflation? What are the initial conditions of the matter-power spectrum? Is there non-Gaussianity? What is the inflationary potential? If you look later on in times, during the matter-dominated era, what is the nature of dark matter? How does the neutrino mass impact the clustering of small scales? And then at late times, what is the local expansion rate? And what is the nature of dark energy? If you're an astrophysicist, you might be interested in some of these intermediate times for other reasons. Namely, what did the first stars and galaxies look like? When did they form? What were their spectral properties? And how did their enrichment, ionization, and heating of the IGM set the stage for the emergence of stellar populations as we know them today? So there's lots of reasons to go to higher redshifts and intermediate redshifts. And the question is, how do we actually tap into this information? So if I plot this in a slightly different space, not in log space, it kind of highlights the fact that there is a substantial amount of redshift space that we have yet to explore. Like I said, we've kind of tapped the early universe and the late universe with the kind of standard LCDM probes. It is true we're learning a lot about the high redshift universe with HST, JWST, and future space missions. Some of these, however, are very narrow surveys, right? They're not going to systematically map out structures at high redshift. And so there is a need to look at alternative probes. One of the most promising probes is known as line intensity mapping or spectral tomography. And what's really neat about this is that it gives us access to large scale modes and also a wide range in redshifts, unlike any other probe. So I'm sure you've heard a lot about LIM from Joaquin and some of the people that work here. Just to recap, what we're doing with line intensity mapping is instead of resolving individual sources and putting a fiber down and measuring the spectrum, we're kind of slewing our telescope across the sky and integrating the total amount of photons that are collected in each pixel. So as a consequence, we make a kind of smooth version of the galaxy field, but we're able to scan the sky much more quickly. So we can much more efficiently probe large scales in the sky. And the other added benefit is that because we're targeting narrow spectral lines, we automatically get high precision redshift information. So with the angular dimension and the line of sight dimension, we can reconstruct three-dimensional structures as a function of cosmic time.
So what makes this different from just a wide angle search?
Yeah, so one is, like I said, is the ability to map these very efficiently. So you can map at very fast speeds.
We're just using a coarse spatial resolution.
Exactly. Yeah, so we are smoothing it, but as a consequence, you're slewing your telescope and collecting all the photons. You can map very large parts of the sky very quickly and generally much more cheaply. You don't have to fiber assign all these, do all this fiber assignment and then make new plates and build these gigapixel cameras.
Well, but it's spectral, it's a cube,
Okay,
not just a wide angle survey,
okay,
right, it's a cube.
sure, but,
Yeah.
okay.
So yeah, exactly. So the other element there is you get the redshift information for free because we're targeting spectral line. So just based on the frequency with which we observe, we know it's resonant frequency, we get that. And typically with these spectral lines, it's very precise.
In order to get enough photons and have a fast enough mapping speed, I guess you have a very poor angular resolution, right?
In some cases, yeah, depending on the telescope design, but yeah, that's generally the trade-off. Yeah. Right. Okay, so this is the idea, and as a consequence, we're mapping the FAIN-10, the FAIN-10 of the galaxy population. We're collecting all those photons, right? We're not trying to actually detect or resolve individual galaxies. Okay. Oh, yeah.
Brian Fields has a question online.
Yeah, just to see if
Uh,
I'm following, is it also the case that over the spectral range you're looking at, the line you're looking at has to dominate the emission?
That's right, indeed, and that is exactly what people like Joaquin are fighting. In 21 centimeter, we don't fight this as much. There's not a lot of interloper lines, as we call them. We have our own set of challenges, which I'll talk about. But it is true. One of the foregrounds for what I'm showing here, our nebular emission intensity mapping, are interloper lines from other redshifts that are redshifting into the band you're observing. That's right.
I'm not
Got it.
part of it, big C plus.
Yeah, sure. Yeah, that's right. Yeah. Indeed. The CO letter in particular is troublesome. But so that's right. So you pick certain lines that you know are perhaps less contaminated, or they are the dominant contribution at those redshifts. Yeah. But in general, there is a wide range of lines in the millimeter and IR you can target, and so there are a number of currently running, planned and funded experiments, including TIM, which Joaquin is leading out of UIUC here. And so there's a lot of excitement about trying to actually tap into this cosmological information, spanning a wide redshift range on the x-axis and a wide field of view range as well. Okay, there's another way you can do this though, and this is the focus of what I'll be talking about today, which is by using neutral hydrogen, right? Why neutral hydrogen? Well, one, it's everywhere, right? It's the most abundant element in the universe, and as a consequence, it gives us an unprecedented redshift range over which we can trace the growth of structure. As we all know, we've used it in exquisite detail to map out the structure of galaxies in the local universe. We can also observe it at cosmological distances. And that is what we call line intensity mapping, or 21 centimeter cosmology, is trying to use 21 centimeter as a probe of large scale structure at cosmological distances. What I'll be talking about today is going to be mostly at higher redshifts above 6. So above redshift 6, the 21 centimeter signal is coming mostly from the intergalactic medium. This is the space between galaxies where the universe is still quite neutral. The first stars had not completely ionized it. After redshift 6 or 5.5, you see most of the H1 is locked in the ISM, and it's effectively like a galaxy survey, an unresolved galaxy survey. Okay. Just like the millimeter and IR intensity mapping, there are a wide range of experiments that have already been funded, that are taking data, and of course that are being planned, like the SKA, that are going after this rich signal. I'll be talking about one of the experiments I've worked very heavily on at higher redshift, called Kern, but there's a wide range of experiments going on right now. Okay, I'm going to skip over a little bit of why to go to cosmology, why to go to high redshifts for the cosmology. I'll talk a little bit about the astrophysics. So as we probably know, there's a lot we don't understand right now about the first stars, the first compact objects, cosmic dawn, and the EOR. So this is a kind of a classic visualization of the EOR. So what you're seeing is the neutral gas that's in dark red being penetrated by these ionizing photons coming out of the stellar populations at redshift 6 and above. As reionization progresses, what you're seeing in blue are these ionization fronts, and what you're going to be left with are these bright galaxies, which we're directly observing now with HST and JWST. But what we also would like to know is can we understand this process by looking at the gas surrounding it, right? So there's a lot that's missed by optical and IR by just looking at this galaxy field. One of the things that we don't really understand is that at very high redshifts about above 15 and 20, when did the first stars form, right? We haven't actually seen POP3 stars yet. What were their spectral properties? What did the first X-ray emitters look like? And then how did this process happen? And how does it relate to the emergence of the galaxy populations coming out of the EOR? So by studying the gas surrounding the first stars and galaxies, we're going to learn a little bit more about this as well. It's quite complementary. Yeah.
Why did you say X-ray, not UV?
Both. So in this case, it's the ionization is driven by the UV. But as I'll say in just a minute, we can also learn about the temperature of the IGM, and the temperature is regulated mostly by X-rays. So the ionizing photons basically stop in these kind of glorified strong-grain spheres.
Yep.
It's the X-rays that penetrate the IGM. That's right. There's a lot to learn there. Okay, so what do we know about cosmic dawn, right? So for going on close to 20 years now, we've known that the EOR, that the ionization of neutral hydrogen, is ending around redshift 6, right? We can see the increasing IGM opacity from high redshift quasars. We know just from the optical depths to the surface of black scattering from WMAP and Planck that we think that the neutral fraction is increasing rapidly around redshift 6. But there's been a lot of contention about what exactly is the global neutral fraction as a function of redshift, and the impact that could have on tau, and as a consequence, cosmological parameters. Of course, just over the past couple of years, we're actually seeing the brightest galaxies coming out of the EOR from JWST. But what's interesting is that this has raised new questions as it's beginning to answer old ones, right? So one of the things that we've learned is that there's an overabundance of bright galaxies relative to our cosmological models. So if you calibrate redshift 4 through 8 UV luminosity functions, and then just extrapolate them to higher redshifts, what you find is that there's kind of an overproduction of bright sources. Now, there's kind of a bevy of theoretical explanations for this. One of the perhaps most simple of them is that there's bursty star formation. I think the jury's still out. But one thing, if you take it at face value, what this implies is a photon budget that would end reionization way too early, right? So if you look at the neutral fraction implied by some of these numbers, you get the EOR ending at redshift 8. And that, of course, sets the optical depth way too high to be consistent with CMB measurements. So there's something of a photon budget crisis. One thing that's uniquely sensitive to the total photon budget is the gas surrounding those 4 stars and galaxies and the 21 centimeter emission. So just to give you a sense for what that looks like, this is a simulation from one of the most state-of-the-art rad hydro simulations from Cosmic Dawn. This is coming out of the MIT group, the THESAN simulations. You're actually looking at the 21 centimeter brightness temperature signal as the EOR evolves, and you're looking at the power spectrum at the top right there. So you can see that there's a lot of information encoded as this process goes about in how these stars are turning on, how they're impacting their environments, and we can learn something about how this process evolves directly from the power spectrum as well. Okay, so to get into a little more nitty gritty, what are we actually sensitive to with 21 centimeter emission? So if you do all the radiative transfer and you kind of distill it down, you get something that looks effectively like this. So you get the signal that we actually measure on the left, this brightness temperature, is proportional to 3 or 4 main quantities. The first is the neutral fraction. If the gas is ionized, i.e. the neutral fraction is 0, we don't see any spin flip. We see no hyperfine coupling. We see more signal when there's more gas, so it's proportional to the matter over density, and then it's also proportional to this interesting combination of the CMB photon temperature at that redshift, so it's the backlight photon temperature, and the spin temperature of the gas, which is the Boltzmann temperature that sets the relative level populations between the singlet and the doublet, triplet, and then but at these redshifts we're talking about, it's effectively coupled to the gas temperature. So you can think of TS as the gas temperature. So we can get cosmology from the 21 centimeter line at cosmic dawn from the matter over density. It's just complicated by all the astrophysics going on. So if you're an astrophysicist, that's great. We can learn about the photon budget and the things that are ionizing the gas and that are heating the gas through this line. Okay, and here's just another plot to show this complementarity. So this is somewhat of an outdated forecast now from some years ago, but this is showing you a forecast with JWST luminosity functions and the constraint that it implies on the faint-end slope of the UV luminosity function. So JWST is not going to measure the faint-end slope turnover, right? There's going to be some amount of extrapolation. Of course, this is where we think most of the photons come from in driving the EOR. But like I said, 21 centimeter is sensitive to something like the integral of the luminosity function. So when you combine these probes, you get a much tighter constraint on what's going on at high redshift. Okay, so let's talk about a power spectrum. So as a cosmologist, we often work with summary statistics. This is a plot of the sensitivity. These stat functions are sensitivity curves for some of the existing 21 centimeter experiments. And one thing that's readily apparent is there's a wide range of astrophysical theory parameter space at high redshift. We don't have a lot of direct observables, and so there's lots that you can do if you're a theorist. And one of the things that we'll do with a high significance power spectrum detection is discriminate between some broad theoretical models. So if you assume a fiducial model where low mass galaxies contribute the dominant photon budget, you get something like this red fiducial model. If you, for example, have some exotic scenario where large mass halos have some outsized contribution, then that changes the clustering of the signal and thus changes the power spectrum, and you get a slightly different signal. Likewise, you can throw in some kind of exotic cold dark matter annihilation that maybe produces some high energy photons that then heats the gas. That also changes the clustering statistics and thus the power spectrum. So we can begin to kind of discriminate broad scale just with the power spectrum. If you go a little more nitty gritty and you kind of adopt some kind of theoretical model, say some cosmological simulation, or in this case, a semi-numerical simulation that has subgrid parameters for these first stellar populations, you can begin to kind of become a little more precise. So this is a forecast that was done a little bit ago, but it still is roughly accurate with our existing understanding. So there's a couple parameters in the semi-numerical model that governs how efficient are these first stars and galaxies at producing UV photons, converting baryons into photons. That's true for the UV photons and the X-rays. And then there's some kind of there's a stellar feedback parameter that determines when do low mass halos basically quench themselves. And what you find is just with 21 centimeter, either with like a Hera experiment, like I'll talk about, or with the futuristic SKA, we're going to begin to learn these parameters to roughly 10%. Okay, and right now these are basically unconstrained at high redshift. So this is very exciting. But one thing we can ask ourselves is how can we improve upon this a little bit? So this forecast took about a month on an HPC cluster. These semi-numerical simulations are faster than the CSAN simulation, which took probably like 1 million CPU hours. These take maybe a couple dozen CPU hours, but doing a brute force MCMC is still very expensive. So during my PhD thesis some number of years ago, one of the things that we looked at was, can we begin to incorporate some machine learning to help accelerate this process? This is now very standard in most areas of cosmology. But at the time, this was the first time that we had done this for 21 centimeter simulations. So this is the same 6 parameter space I was showing you before. But one of the things we couldn't do is we couldn't vary cosmology. Because when you vary the cosmology, you had to rerun the density field, and you have a higher parameter dimensionality, so your MCMC chains take too long. You know, the astrophysics alone took a month. It could have taken 2 or more months to do both. So if you can develop some kind of machine learning technique to accelerate it, not only do you do the inference faster that you wanted to do, it now opens you up to looking at constraining more physics that you couldn't do before. So as maybe some of you are familiar, one way to kind of speed this up is instead of using your simulation in your likelihood, you can learn some kind of low dimensional mapping between the parameters you care about, i.e. the astrophysics or the cosmology, and the summary statistic you care about, i.e. the power spectrum. So in this case, we just trained a generic Gaussian process simulator, and voila, we can both do the astrophysics and the cosmology jointly. We can speed this up by 3 orders of magnitude. One of the things that's important is if you want to get cosmology out of cosmic dawn, you have to marginalize over the astrophysics because it's all kind of muddled together. And before, we had always been confined to using analytic approximations, making assumptions about the spin temperature. Now we can just do this kind of with a full-on cosmological simulation. And I'll note this is, like I said, this was pretty standard in cosmology widely, but had never really been applied to 21 centimeter at the time. Now it's fairly standard. So it's really taken hold in all areas of astrophysics. Since 2017, there's about half a dozen 21 centimeter emulators. And these are all pretty much in the same vein, taking parameters that you care about, say, cosmological parameters, LCDM, astrophysics, and mapping it to a statistic, like a single number. If we ask the question, what's the next leap in AI-driven inference for cosmology, particularly 21 centimeter, I think it's going to be something a little different. And I'm not going to talk about it today, but maybe in the Q&A.
So why so many emulators? I mean,
because this uses a Gaussian process, this uses a variational autoencoder, this uses a LSTM. There's one that just uses these Kolmogorov-Arnold neural networks, different architectures. They have slowly been increasing in accuracy. The trade-off with the Gaussian process is you don't get the great uncertainty quantification, which every time I review one of these papers, I always really stick it to them. But they've been improving in accuracy, for sure, yeah. Okay, so I'm gonna kind of transition now to talking about the actual, how do we make these measurements and why is it so difficult? Let me make sure I'm still on time. Okay, so something you may not be aware of is that for all the excitement that we have around 21 centimeter, an unambiguous direct detection at high redshift still eludes us. So we've made some kind of tentative detections, like the edge signal that later we think now is probably a systematic. But particularly at high redshift, talking about an interferometer, so measuring the power spectrum, we do not have a direct detection. And as you may know, it's because we have very bright non-thermal foregrounds at these very low frequencies at 100 megahertz. But it turns out this is not the only problem. If this were only the case, we would have direct detections. We would be doing most of the science that we want to do. The problem is this coupled problem. We have really bright foregrounds and an imperfectly known instrumental response. And it's that combined problem that has been tough to crack. So let's go into it in a little more detail. So if you think about our image cubes, and this is in our projected into cosmological space. So this is X, Y, Z in co-moving megaparsecs. Foregrounds, because they are spectrally smooth, in an intensity mapping perspective, look like they're smeared out along the line of sight, right? They're not inhomogeneous, they are spectrally smooth. Noise is basically Gaussian, and the 21 centimeter signal is highly spectrally variant because through the line of sight, you're probing the inhomogeneities of the IGM. So let's just take a naive power spectrum estimator. Let's form our image cubes and take a three-dimensional Fourier transform. What we're saying is that the foregrounds have a compact support along the line of sight. They occupy small, low Fourier modes. Whereas the 21 centimeter signal occupies a wide range of modes, but in particular at high K line of sight and K parallel, it should be foreground free. So we just measure the signal there, right? And like I said, if that were the case, then we would have high detection measurements. That's not the full story, which I'll go into a little bit. But okay, so circa 2022, this is basically what the landscape looked like. These are the best upper limits on the power spectrum from the variety of telescopes that I briefly mentioned. And one thing that you can see is that over the past 5-10 years, we've made steady progress in marching down in this parameter space and setting tighter and tighter constraints. Now, again, we are a couple orders of magnitude away from this fiducial theory, but we're making quite good progress over the years. Okay, so what do we think is going to get us those last couple orders of magnitude? Well, one of them is we think is Hera, or the Hydrogen Epoch of Reionization Array, which I've worked extensively on. This is an interferometer in South Africa, right next to the Meerkat array right there. That's the SKA mid-pathfinder. So Hera is a compact interferometer. It's roughly 350 individual 14-meter dishes with the collecting area of roughly Arecibo. It observes from 50 to 250 megahertz, which for the 21 centimeter line allows us to probe cosmology from redshift 5 all the way up to roughly 25. It has a very narrow redshift resolution due to the frequency channelization, but it has, again, a somewhat wide angular resolution. We're measuring fairly large scales, in part because our interferometer is compact, right? So a compact baseline collection means large angular scales, but we measure a very wide field of view as well. So it is a kind of scan survey-like experiment where we don't point the telescope, we let the sky pass overhead, and we map out a wide stripe on the sky. So a lot of my PhD and some of my first postdoc was in developing the analysis pipeline for this first season of data, which we took in 2017, and some of the subsequent analysis. I would love to have time to go through some of the systematics with you, because this really is where our bottom line, that's where we move our bottom line, is by looking at systematics. Most of those limits that I showed you there are not noise limited, they're systematics limited. So we have more data, but we've hit a plateau. So you gain the bang for your buck in doing better systematic modeling. And that was most of my PhD and some of my first postdoc. But this is basically, in a nutshell, what we're trying to do. This is a line of sight power spectrum as a function of LST. So think of this as the power spectrum as pointing on the sky. We have this compact support in the foregrounds, and we have noise. We have these systematics that are throwing power. So one of the major developments that we've made over the past 5 years is using simulations that inform us as to some of the phenomenology of the systematics if we have some basic understanding of what's going on. In this case, what we're finding is basically coupled crosstalk between antennas. We can simulate that and we can look at its phenomenology and we can construct custom filters to try to reject that. And in this case, we were able to do that down to the noise. Now, this is crucially paired with validation simulations, right? Because we don't want to subtract the cosmological signal in the data. So one of the other big developments that we've made over the past 5 years, I'm sure Joaquin, you know very well, is in our end-to-end pipeline validation, right? So one of the things we did is we have the realistic mock signals on the sky, we corrupt them with systematics, and then we push them through our analysis pipeline to reconstruct some known, a priori known power spectrum. So this has been a big effort. And one of the cool things that we discovered with this is we discovered a roughly 10% bias in our pipeline. So the first time we did this was off by a little bit. And we said, what's going on? And we dug into it and we discovered that our absolute calibration pipeline was in some cases working with higher noise, lower SNR data than we thought. And we were using an algorithm that in the low SNR regime was a biased estimator. And that just brought everything up a little bit. So we were able to fix that and correct it before we published this work. Okay, so that all culminated in our first limits for Kern, which we took 2 redshift bands, one at 8 and 10.5. And those are those pink triangles. They are the best limits to date, and particularly at redshift 8, they're over an order of magnitude improvement. But this was with about 15, 16 days. We went back with basically the same pipeline, and we analyzed about 100 days, and we got about a factor of 2 better. So it turns out 5 times more data does not mean 5 times better limits for various reasons, but we were able to improve by a factor of 2. Which means that we're not quite systematic limited. We're still thermal noise limited. More data means better limits. Yet we're still about 2 orders of magnitude away. Why is that? Well, in part because that data set was when we only had about this much of the array. So that's why, and we've now built out the entire thing. So we're now taking data with basically the entire array, and the sensitivity goes as the number of antennas squared. So we have vastly more sensitivity now than we did 5 years ago. So we expect to be able to be in that interesting regime. Yeah.
Well, only the probe 8, is Hera just tuned to the redshift of 8? Will you be able to pull along
Yeah.
other
It's a
places?
great question. Without going into too much detail, we can measure the signal from redshift 5 to 25. There's various things why in certain redshift regions, which corresponds to frequency bands, we don't want to measure the signal because there's lots of RFI. So there's lots of radio frequency interference from satellites, from digital TV, from walkie-talkies. So the SKA mid is right next to us. They operate at different frequencies. So their walkie-talkies operate in our band, and we're not allowed to have our walkie-talkies operate in their band because they own the site. So we've had some issues, it's kind of a process, but we're in the Kru desert, so it's fairly radio quiet, but there still is RFI. So that's part of the reason why you're seeing that. But we're coming out with some new limits in the next couple of months that are going to push this to even higher redshifts. Okay, so let's talk about what we've learned. So it turns out we want to make detections, and we're getting very close to that. We can already do some interesting science just with these upper limits by ruling out some of this parameter space. And this mainly comes from what Joaquin was saying, which is the heating of the gas. So this is really what we're going to be able to constrain. So let's look at the evolution of the thermal history of the universe. We know that the CMB temperature falls off like a scale factor. At some point, the gas decouples from the CMB photons and begins to cool adiabatically. That's the orange line. At some point, stars form, they ionize the gas and they heat the gas, and that drives the kinetic temperature of the gas up to very high values above the CMB temperature. We call this the X-ray heating epoch. We know very little about it. However, there are models where perhaps this X-ray heating epoch is delayed, perhaps structure formation is delayed, or perhaps this heating is inefficient. Perhaps these X-rays can't really escape the ISM, and they don't really make it into the large-scale IGMs. There's plenty of parameter space to allow that to happen. So it turns out, if you go back to this equation here, that if you have a very low gas temperature, very low spin temperature in this case, that drives this whole value to be very large. It's negative, but it's very large. That makes the fluctuations, i.e. the power spectrum, very large. So it's these cold IGM models that we can begin to directly rule out with these more sensitive upper limits that we could not really do with these ones up here. Okay. So if you take those cosmological simulations I told you about and you forward model them, one thing you can do is you can look at the average temperature of the gas in simulations whose power spectra are above our upper limits, right? So you can maybe carve out what is this posterior of the average temperature of the gas. Now this is and if you look at the parameters, they're very correlated because we don't have a detection, but you can begin to say something about the gas temperature at redshift 8. And one thing you find is that in the prior volume, which includes in this time it was HST UV luminosity functions, and then information about the opacity of the IGM from quasar spectra and the CMB optical depth, there's lots of models where the temperature of the gas remains quote unquote adiabatically cold. It's just been cooling since it decoupled from the CMB, nothing has heated it. This is that gray line, this is that prior volume. And for the first time, we can actually begin to say something about the IGM, the temperature of the IGM at redshift 8. And in this case, we're able to rule out at 95% confidence that it is adiabatically cold. Now you can turn that around and say, well, if the gas is hot, something heated it. So in a somewhat model-dependent way, i.e. the semi-numerics of this cosmological simulation, you can begin to say something about this X-ray production efficiency parameter of these first X-ray sources. And the TLDR is, with all of our existing evidence prior to the Hera likelihood, we have very little constraint on the X-ray production efficiency of high redshift X-ray sources. With the Hera likelihood, we can now begin to say, yep, they have to be more efficient in order to heat the gas. And one thing we can say, which is quite interesting, is that if you look at high mass X-ray binaries in the local universe, they tend to have efficiencies around this value that's consistent with a higher metallicity population. We know in the high redshift universe, things are at lower metallicity. And as a consequence, they're hotter and they're more efficient at producing these X-rays. And for the first time, we're actually able to favor something which we theoretically think should exist, but till now have had no empirical evidence to really suggest that, yes, these sources at higher redshift probably have a lower metallicity.
So do you also have versions of this where you include weird radio backgrounds?
That's right, we do, yeah, and that does degrade these slightly. The radio background has been somewhat controversial, and there's been other evidence to suggest that the high radio background probably isn't what's going on, but we do have some plots as well. Yeah, I can show them later if you'd like, yeah.
What was the
Can you explain?
high radio background meaning more X-rays heating or what?
Yeah, I can show you right here. So one way to make this guy big by making this guy small or that guy big. So if the background source is the CMB, we think we know that pretty well. But if you have really active AGN or something that's producing another source of background photons, that can also drive this to be very large as well. Yeah. But you have to have something that's very, very bright in the background. Great question. All right. So what's coming next from Hera? Right, so that was phase 1. Phase 2, we have an entirely new front end, new feeds, new analog system, new amplifiers, and we have crucially more antennas, like I said, and our sensitivity scales as n squared. So what we're going to be doing is in this plot, we're going to be pushing down sensitivity, but also crucially to higher redshift, because our new front end allows us to go to lower frequencies, i.e. higher redshift, where there's even less that we understand. So this is very exciting, and we actually have some analysis that will be coming out in the next couple of months. So stay tuned for that.
What's the diagram on the left there? Above?
Yeah, this is our array, and I think this is actually about a year and a half old, outdated, but this is how many antennas we actually had plugged into our correlator. Yeah, and we plug them out and plug them back in depending on what's going on. But this is basically how much of the array we're observing with. That's even more filled out now.
And this larger coarser array, what's that?
Yeah, so we have a core, which I showed you before. That's where our main sensitivity comes from. We have these outriggers to get, for any of the interferom radio astronomers here, we have outrigger antennas to get higher angular resolution for some imaging. But you'll notice we don't have a lot of them. So the UV, the filling of the UV plane out here is not very dense. We don't get a lot of sensitivity to the 21 centimeter signal, but we can use them to image Fornax A and understand some lobe structure and maybe do some diagnostics. And it's kind of a technology demonstrator. We have them, we use them, but they don't really give us anything in terms of the sensitivity to the power spectrum. Yeah.
So what's the theoretical lines of this figure, and how do we that operations can distinguish this theoretical line?
Down here, these black lines?
Yeah.
Yeah, so these are some of the theory predictions. If you look at the prior space for those astrophysical parameters I told you, which are quite wide, you can sample from the parameter space and you can run the simulation forward, and this is what you get. So the way you begin to distinguish between those lines is through inference, through parameter inference. This is the standard way we do this is with MCMC, forming a likelihood, carving out.
Why some have some peaks, the redshift peaks?
Yeah,
Is there any physical meaning?
there is, yeah. So just like in the CMB, how we have these really great peaks and troughs, which give us the acoustic scale and then the harmonics about that. There's something similar going on here, but it doesn't have to do with angular scale. Some of these bumps have to do with what's going on with the gas. So there's a couple of bumps. This last one is the reionization bump. So bubbles are beginning to form and grow, and so you see that in the power spectrum. That's the kind of movie I showed you where the power spectrum was fluctuating. There's kind of the X-ray heating bump, which kind of come up here, so that the gas is being heated, and that causes. And then there's the kind of line enough coupling bump as well, which you get, which couples the gas temperature. So they do relate to kind of physically meaningful eras in the formation of these first stars and galaxies and their impact on the IGM. Yeah, but we tend to just lump it all together in terms of this inference package and then infer it all in one go. This is a sneak peek. So we have, this is phase 2 data. This is our most sensitive data. This is only one night of data. What you're seeing on top is a mosaic that I made of our Hera strip that we call. You can see Fornax A right in the middle there. What you're seeing over here is side lobes from the galactic plane, which is not in our field of view. It's in our side lobe, but it is so bright that its PSF gradient lobes rain into our field of view. And then what I've done is I've applied some of these systematics filters that I described, which is the basis of a lot of how we understand systematics and reject them. And you can see some residuals, so that's like a grading lobe of Fornax A. But to a large extent, and then this is a thermal noise draw from our noise covariance. There's some residuals which we're aiming to understand, but there's parts of the space that look fairly noise-like. So this is exciting. So this is what we're pushing on now, and we'll have something to share soon. Okay, so in the last couple minutes here, 4:30-ish, is that right? I'll go through some of this, what I've been working on, what I think is particularly exciting. I might kind of skip through some of this. Okay, so I've talked a lot about upper limits. How do we set upper limits? You know, it's somewhat straightforward. How we go to a detection is much more complicated, statistically speaking. So, a rough overview. What's in our data? So this is an example of what our data looks like in Fourier space. So if you just take a Fourier transform along the line of sight. There's basically three components. We have foregrounds, non-thermal synchrotron, we have noise, which is basically flat, and we have an EOR signal, which has broad support in Fourier space. Right? This is the foreground avoidance paradigm that I mentioned before. The name of the game is taking more data and integrating this noise down, right, to make a detection. So we want to aim for noise until we see signal. But how do we distinguish between signal and systematic? That is the key question. And like I said, if this were the case, we would already have measurements of this power spectrum. What happens is that we have an instrumental response that's multiplicative in nature. So in Fourier space, with the convolution theorem, it's a convolution in Fourier space. So we have some instrumental kernel in red that convolves this blue line to something that's much more precarious. And there's uncertainty in that red line, right? If we change minor details of the instrument or of our RFI sampling pattern, we get different kernels. So what we actually measure is that red. We throw out a lot of these low Fourier modes because we know that they're intrinsically contaminated, and we try to make measurements outside of that region. But when we see systematics, which we know exist, we just say, well, this is probably systematics. Why don't we just cut a little more, right? But obviously, you're going to run into a real signal at some point, and that's not a real robust way of setting, making a detection. And that's a somewhat of a simplification. Similar to the CMB, we do a lot of jackknife tests and null tests to try to understand the signal that we're measuring is either on the sky or if it's crosstalk in our array. But a jackknife test is not going to tell you what you've measured is a signal, a cosmological signal. It might just inform you that, oh, this has some weird phenomenology that's not really cosmology-like. So it's not a really robust way for confirming a detection. How would we like to do this? Well, we want to understand, intrinsically, we want to understand that kernel and its uncertainty. So what we'd like to do is make measurements, but then place really robust error bars, which we have never been able to do. The thing that we're really good at is understanding our noise error bar, but we have no way of propagating our uncertainty on the foregrounds through our data model and onto our estimator, coming from the foregrounds and from our instrumental response. And that's in large part because this is a highly high dimensional nonlinear inverse problem. Okay. So what I've been doing is trying to unpack some of the recent advances in ML, AI, hardware and software to build a kind of new modern differentiable Bayesian forward model for 21 centimeter cosmology. And it's tuned for 21 centimeter, but it's equally applicable to any limb tracer in reality. And what the idea is that we basically parameterize all the signals that go into our data in their native space, i.e. on the sky. You run this large integral, which is our forward model, basically what the telescope sees. You form your data product, which are these visibilities. You form a likelihood given your raw data in a noise model. And then you crucially incorporate any priors you have, right? So we can have priors from other surveys of the foregrounds. We have prior understanding of our instrument from our lab measurements, from say drone modeling of the response of the beam. And then we sample and optimize that space. So you can think of this kind of as like a machine learning optimization, but using the posterior or the negative log posterior instead of some generalized loss function. Why is this great? Well, it's really easily GPU portable. You just do model.push to the GPU and everything runs on the GPU. And the auto diff, what it does is it gets you the gradients of the posterior with respect to your parameters. And now you can begin to stick this into gradient-based sampling and NCMC techniques that scale to high dimensionality. So I'll run through an example of this real quick. So this is a proof of concept that I did. This is the most ambitious forward model that's ever been attempted for some kind of forecast like this. This is a full sky foreground model using roughly 40,000 spherical harmonic modes for the foregrounds, roughly 50,000 spherical harmonic modes for this EOR signal that we measure in small stripe. And then we use a couple hundred parameters for the beam. And there's a reason why there's a lot less for the beam, which I can talk about later. But then we adopt some kind of physically motivated prior. So we know something about the foreground sky from the kind of legacy of radio surveys. We know them to roughly 10%, which is not 1 part in 10 to the 5. It's 1 part in 10 to the 1 or 2. So we know it's roughly 5%. So we can adopt some priors based on that. We know something about the beam from our instrumental modeling. So we can incorporate roughly 1 to 5% priors on our beam. And we give very wide priors for the 21 centimeter signal. Let me talk about one of the major systematics we face and how we're modeling this. So one of the major systematics that we face is the response of the beam. So this is what our beam looks like in kind of elevation and azimuth. If you slightly change the location of the feed, you change the response of the beam by some percentage, right? This is not 1 part in 10 to the 5, it's 10%, right? So the foregrounds coming in are now modulated by something that's 10%, so you get 10% foreground errors. We can't predict exactly what this looks like, but you can see that it has some kind of structure that's bounded, right? So you can understand that maybe this is well modeled by a spherical harmonic basis. So this is what we do. We throw these degrees of freedom at it. One of the things that I did was to come up with a new spherical harmonic formalism that is orthogonal and complete on the cut sky as opposed to the full sphere. And that means that we can compress this parameter dimensionality by a lot. I'm not going to go into that. It's in the paper. Happy to talk about it if there's questions. But one of the things we do is we adopt a physically motivated prior for the beam. So what we think we know is that if you're looking at boresight along the beam, we think we know it pretty well. As you go off axis, weird things start to happen, and we really don't know what the beam is. And so the prior that we adopt basically says, at boresight, we know the beam pretty well. In the far side lobes, it's anyone's guess. We know it's ordered unity. And this is basically how we would like to incorporate prior information on our instrumental terms. And you can do that in this kind of end-to-end forward model. This is the optimization. A really interesting thing is that the optimization is not terribly hard. The sampling is extremely hard. And they're kind of related, but this is a much harder problem. How do you sample from a high dimensional and highly correlated space? If we had solved this problem, if this problem was just in theory solved, then all of our neural networks would be Bayesian neural networks and we'd have a lot easier time working with them. It's not a very difficult problem. And so how do you sample from a 100,000 dimensional space? I won't go through that, but basically we use a modified version of HMC with low rank block diagonal versions of the mass matrix to do this. And these are the chains you get, and this is the sample lag. If you didn't use that mass matrix, you would see that these have really intense autocorrelation, and this would still be intractable, even with HMC. So using this preconditioning actually makes this tractable. And you know, you can look at the MCMC parameters, or these chains on each one of the 90,000 parameters. It's not really informative. So instead, we can look at the posterior projected onto the various components, like the beam. So in the last minute here, this is the perturbed beam that we a priori did not know. It's very different than our smooth fiducial beam. And these red lines are draws from that marginal posterior. Something that's really cool is that if you don't do the MCMC varying all the parameters and you just vary the beam parameters, i.e. you condition on the foregrounds, you get that blue one. And you say my uncertainty in the beam is really tiny because I'm conditioning on the foregrounds. If you vary all the parameters, you say, oh, I have an inflated posterior. What this means is that the marginalization is actually working. There's some communication, so there's a degeneracy between the foregrounds and the beam that if you didn't do this full MCMC sampling, you would be overestimating your uncertainty, underestimating your uncertainty on the beam. Okay, so you can go through this. This is like posteriors at the field level. So now you're reconstructing the full posterior for every single pixel on the sky and its covariance matrix. These are sight lines. And what's great is you now have the posterior at the field level. You can do field-based inference. You can project it onto 1 point, 2 point, whatever summary you like. This is the power spectrum, which we know and love. And this is the recovered power spectrum uncertainty relative to the true power spectrum. And this is the last slide. What we've never been able to do is to understand what is that marginal uncertainty in the power spectrum at low K, right when you get close to that foreground linkage. We've always been good at thermal noise error bars. We've never been able to do that joint error bars. So this is the first time that we've been able to actually propagate the foreground and instrumental uncertainty jointly onto something like the power spectrum. And the last thing is really cool. This is now running on UIUC's Delta cluster. One of the things that is not clear is whether this will scale to the large interferometers that are going to make some of the most exciting science cases going forward. I think that we've got a good shot at it. It requires GPU acceleration, and there's lots of room for improvement. But one of the things that I'm doing right now with an NSF computational grant is trying to scale this up to the 1,200 of GPU scale with you guys' great cluster here. So that's basically it. What I've described is a kind of a framework through which a lot of different kinds of analysis will become available that open up a more Bayesian rigorous approach. One of which is this joint end-to-end inference I talked about, but another is a lot of things that apply to, for example, other limb applications like beam modeling, calibration modeling, and then joint inference. So with that, I'll close. Yeah, I hope I've talked a little, convinced you that that there's a lot of exciting things going on in the limb space right now, particularly at high redshift, talking about understanding what's going on at cosmic dawn and the complementary with JWST. We're really close to making a first detection, and just stay tuned. Thank you.
Oh, right, we have time for questions. Spencer?
So on here, we had a plot of 4 stacked images. They're blue, green, and yellow. The top level was
The real data.
analysis. There are patterns in that. What are they? Is that a systematic of the array? Why are they stacked in 3?
That's a great question.
What is you referred to that yellow dot by name? Is that a bubble?
So this is a really bright, this is one of the brightest radio galaxies that we see. It's called Fornax A. It's an active radio galaxy, so it has these jets that have these ionized plasma that creates a lot of synchrotron emission, and we see it really bright in the radio. That's this guy right in the middle. So with interferometry, when you make an image of the source convolved with your point spread function. So those little dots are the point spread function of Hera, which are really nasty because we don't fill out the UV plane uniformly. We have this really redundant hexagonal configuration. And so you're seeing that hexagonal configuration reflected in the point spread function. But Hera is not an imaging array. It is a redundant power spectrum, visibility based. That's how it's been designed. And that's in part why we've made such deep limits relative to some of the other imaging based arrays.
I mean, is there only supposed to be one object in this
That's right.
field?
Yep, yeah. So if you've ever worked with like radio data, like if you've used CASA, what you typically want to do is deconvolve the PSF, which means removing those grading lobes, right? It requires some knowledge of the PSF.
So, sort of related question. You mentioned earlier that you're on the same site as Meerkat.
Yeah.
And your folks are doing imaging, and a lot of the interesting things that you're doing with the neural network based approach
Yeah.
is combining multimodal data in this case. why not combine data from both arrays? Can you do co-observing with them? Can you use
Yeah.
a combination of both of those two?
Yeah, you very much can. That is basically what we're trying to do right now. So in particular, what you can do is so Meerkat operates at lower redshifts. So we measure different parts of the universe. So we could definitely say something about the foregrounds that we see that are somewhat different, but we're measuring different cosmological signals. What you can do is we have other global signal experiments. These are measuring the cosmic monopole, like edges. This is very much ripe for a joint analysis. Global signal has a lot fewer degrees of freedom. So it's a much more difficult extraction. But if we can set some prior on the signal from the power spectrum, we might have an easier job pulling up model. So that's, yeah, that's right.
And then just to follow up, because I'm curious, this Bayesian approach, forward modeling the signal.
Yeah.
Great, but you also have foregrounds that are effectively time evolving. You pointed out that the radio walkie-talkies or whatever.
Yes,
You have,
yes.
and you said 50 megahertz to 250 megahertz.
Yes.
So that's like FM.
It is, yeah. And that's why we cut everything out of FM. Yeah. So we're never gonna make those FM measurements like, yeah. Like Redshift, like 14, yeah.
So again, about your Bayesian approach, like it sounds like you use physically motivated priors, but then you find that once you forward model, like the model is learning to generate states between your foregrounds and your mean, like parameters and stuff.
Yeah.
And then you derive like once you have your final posteriors, do you think that could later inform your prior?
Yeah. That's right.
Do you incorporate that? Like, how do you?
Yeah, that's right. So for example, the prior I set on the beam comes from some, probably not Bayesian, but some likelihood analysis of the beam in the lab. So we have some measurement of what the beam response is in the lab, and that is what goes into our prior for this analysis. Now, we take more data, or we take data at a different elevation. We have the same beam, different sky. Probably this posterior will go into the prior of that analysis. Yeah.
Okay, but what about posteriors from the same analysis? Do you think that could sort of loop back in like a feedback loop, or do you think that would?
I think statistically that's not sound, but I could be wrong. Yeah.
Also, Brian Fields has a question.
Okay.
Yeah, thanks for your talk. It was really really interesting. I'm an outsider, but I know that one of the dreams for this field is to eventually get measurements from the far side of the moon. And
Yes.
we live in crazy times, and so we have got our own terrestrial problems now. But looking forward to that great day. How will that interplay with what you've been talking about? What will that buy us?
Yeah. So one, it will buy us unfettered access to the redshift spectrum because we won't have to deal with FM. We won't have to deal with sporadic walkie-talkies or RFI. So this age where we live in, where we have to pick these redshift bands very carefully, we'll be able to use whatever we want. And it might be that some of our most constraining modes might be at a particular redshift that we can't access, right? If we're looking about these peaks and troughs in the power spectrum, right? It's those that give us the most constraining power, it's those that maximize Fisher information. We might not be able to use those. So that's the main thing, is we can use all of our band with little concern about RFI, which RFI is always something that we think about when we see spectral leakage. Did we miss some RFI? So it's going to help with that a lot.
Cool. Thanks.
The other thing I'll mention is getting to low frequency. So below roughly 15 megahertz, the ionosphere becomes opaque. You're hitting the platinum frequency. You can't
yeah.
So if you want to do super high dark ages cosmology, which I didn't even talk about, but was highlighted in the decadal Astro 2020 decadal as the golden holy grail of measuring the initial conditions of the universe, you have to go to space or you have to go to the moon. So that is a science driver as well.
Cool. Thanks.
Can you say a little bit more on the constraints that Kern placed on that?
Yes. That's a great question. Sorry. It is a slide that I hid. Sorry, because I didn't want to go over it. But yes, so we are directly sensitive to the gas temperature. Or sorry, to the ionization state. And what that means is that in theory, this is somewhat of an outdated. We have filled this in a little bit with more quasars and some more high redshift measurements. But we're gonna be able to set a very precise constraint on the evolution of the neutral fraction. We're directly measuring the ionization state of the gas. And what, sorry, what that also does, I'm gonna just do this here, I'm not gonna share it, is it's gonna allow us to do immediate cosmology. So, you know, a lot of people look at low redshift to do cosmology with intensity mapping. By understanding the evolution of the neutral fraction, we're basically giving you a point estimate of tau. Now, you might have concerns about the residual systematics, but if you believe the 21 centimeter data, and we're telling you that this is the neutral fraction, you can basically set an independent constraint on tau, which is strongly degenerate with the amplitude of the primordial scalar fluctuations in the CMB. So by doing a joint analysis, which would be, you would need an emulator to do this, which is part of what motivated that study, you can automatically improve constraints on A sub S by about a factor of 3. And it turns out that some of the neutrino mass, it has a similar kind of effect on the TT spectrum. Yeah. So that is a big cosmology motivator for cosmic dawn 21 centimeter.
This is maybe a longer question, but if you were redesigning Hera today.
Yeah.
Same cost envelope.
Yeah.
What would you change?
Couple of things. So one of the things that we did not, I was talking to Hokin about this earlier. Our array is really jam-packed together. It looks like kind of like a CMB focal plane, right? Where is it? It's this hexagonal structure. So these things are real close to each other, and our limiting systematic is over-the-air coupling between antennas. Scatter. So one of the things we're trying to do is, can we modify this lip? Can we feather it? Can we curve it? Can we lower the feed, occult it slightly to reduce that scattering? And maybe spread out these elements a little bit more. Another thing that we're thinking about is putting in some kind of absorbers in between these dishes to try to disrupt standing waves within the array. Same cost, same size, same scale, same front end, same back end, just a slightly modified version that would get rid of that last order magnitude systematics. That's kind of where we are right now. But we came a long way from where we were before, and we're gonna go a little bit more with what we have, and we may get close to direct detection.
Is that a mesh dish?
It is a chicken wire, yep. So it's great so this is meter wave. I mean, it's a little more expensive than that, but this is meter wave wavelengths. You can have centimeter-ish deviations, and it isn't a big deal.
Spencer has chicken, she knows very well.
Chicken wire, standard, industry standard.
Yeah. You can make, there's a great Astro Radio Lab where you can make a radio antenna with like a coffee can. This is like a great Radio Lab 101.
What do you do with a walk?
And I should know this, and maybe you had this on the one of your previous slides where you had a whole bunch of experiments, including Tim earlier
Yep.
on. DSA 2000 I know is higher frequency, which is a lower redshift, but
Yes.
is there sort of any redshift range where there's overlap between these experiments?
Yes, I believe there is a prototype of a higher, lower frequency DSA that may get all the way up. So the OVRL, the LWA is operating here as well, which is run by Caltech. DSA is lower redshift. But yeah, so there are some hints of what's coming next for the US, on the US side. What's going to try to compete with the SKA low.
So you're obviously thinking about big data and analysis techniques. How do you actually want to handle all of that volume of data from these multiple different experiments?
Yeah. So I mean, right now we're somewhat siloed. Like Hera has its own compute, has its own storage. DSA has its own. At some point, we'll want to do cross correlations. That's where we're going to get most of our bang for our buck. That's going to require some politicking. But I think that is the way that we will all go, because that is where we're going to get the most science. And there will be some perhaps Uber consortium, perhaps, who knows? But yeah, that is very exciting.
Okay. Well, if we don't have any other questions, let's thank Nick.
Yeah, thank you.